Everyone, this is day 22 of Python Pro from CDC. Today we are diving into one of the fundamental data structures in Python, lists. Lists are versatile, powerful, allowing us to store and manipulate collections of items. So what exactly is a list? In Python, a list is a dynamic ordered collection of elements. These elements can be of any type. It can be integers, strings, float, or other numbers, or even other lists. So lists are incredibly flexible and provide a convenient way to organize and work with data. So diving deep into lists, one should understand why lists are called lists in Python, but the same arrangement is called as array in other languages. Because when someone says arrays, they actually refer to something called a static array. Static arrays are arrays which can only hold one data type. For example, as you have seen earlier, a list in Python can store different data types, such as one list can contain numbers, strings, and even other lists. But in static array, we can't do that. And in static arrays, the memory capacity of the array has to be declared at the starting itself. So if the starting capacity is assigned as 10, we can't add the 11th element to the array. If we do, it will throw an out of bound error in other languages. But in Python, we call them as lists because they are dynamic arrays. As they are dynamic arrays, the memory allocation is different in Python under the hood. So as you can see here, let's say there is a list with a capacity of 13. So we will be adding items to the list, and if we add the 14th element to the list, you know what it will do? It will multiply the original capacity by 2 and add it to the original capacity. So here what it will happen, the capacity is 13. So what it will do, the additional capacity is 2 into 13, it's 26. And the 26 will be added to the 13. So the new capacity will be 39. So how does Python do this memory, additional memory allocation and stuff? As you can see, here we have got 500 in the memory location, but here we have got 700 in the memory location. Meaning, if we are adding one extra element over the capacity, you know what it will do? It will do a memory overhead and completely reallocate the array to a different memory location. So you might be wondering why we have got 504 after 500 and 508 after 504, and why not 500, 501, 502. So to answer that question, one integer in Python is of 4 bytes. So the 500th memory location is of 1 byte, 501 is of second byte, 502 is third byte, and 503 is fourth byte. So 504 will be the fifth byte, so it is for the second element. So these are the time complexities of various list operations: lookup by index, lookup by value, traversal, adding and removing elements. We will see how those work in detail now. So to perform these operations, we have to create a list first. Creating a list is so easy in Python. We just have to type the elements inside a square bracket. So first thing I'm trying is lookup by index. As we are directly giving the index here, it can directly refer to the memory location of the element. So this is single operation. So there are no iterations involved in this execution. That's why the big O of lookup by index is just O of 1, constant time. So moving on to lookup by value. We will be giving a value, then we will try to find the index of the value. So here we have to, of course, iterate through the list. So the element we have here is 9. It will have to iterate from 1 to 2 to 3, then 5, then 9. So of course it becomes O of n. Let's run this and see what is happening. So of course we got the output as 4, cause 9 is in the fifth position, but it is in the fourth index of the list. So we got 4 as the output here. So What is traversal? Traversal is basically going through every element, every item of the list. Here we can just use a basic for loop to print all the elements of the array. So we have got the result as every element in the array 1, 2, 3, 5 and 9. So as we traverse through each and every element, the big O of this stays at O of n. Now moving on to append. Append is a function we use to add the element at the end of the array. So there is no memory haggling here. We are not reducing or increasing any memory or even iterating through any of the items in the list. So this append function in Python has a time complexity of O of 1, constant time. But then here comes the insert operation. Insert operation, as you can see, append we got 12 added in the last. So we got insert operation here. In insert operation, we will give the index as well as the element we want to insert in. So while we run this, we will have in third index we will have 15. So 0, 1, 2, 3. Third index we got 15 as you can see here. So how does this work and why does it have O of 1 O of n as its time complexity? We can see here. So let's say some number is going to be added in between 33 and 65. So it can be added easily, but this 65 has to go down here. Then this 17 has to go down here. Then 29 has to go down here. Then 16, then 48, then 1 and so on and so on. So that's why we are haggling the memory here. So the time complexity of insert operation is O of n. Same goes for the remove. Remove operation, we will directly remove the element. Let's the element is removed. Let's print the element. Let's print the whole list. See, we tried to remove 15 from the list. There was 15 here and there is no 15 here cause it will traverse through every element searching for 15. So the time complexity is O of n. So let's finish today's session with a problem here. This problem is called running sum of 1D array. 1D array is basically a list. So the question is given an array called nums. We define a running sum of an array as running sum of I is equal to sum of nums of 0 till nums of I. So what is happening here? We have input as 1, 2, 3, 4. The output as 1, 3, 6 and 10. So the first element we have 1. How? We have to add nums of 0 till nums of I, right? Here the ith element is also 0. So we don't have to add 1 with anything. So 1 will directly come here. So then for the second element we have to add 1 and 2 till the second element. For the third element we have to add everything till the third element. For the fourth element we have to add everything till the fourth element. As you can see 1 is 1, 1 plus 2 is 3, 1 plus 2 plus 3 is 6, 1 plus 2 plus 3 plus 4 is 10. Same goes here 1 1 1 1 1 and same goes here 3 1 2 10 and 1 we have 3 4 6 16 and 17. So as you can see from these cases the first element for the in the output and for the output is exactly the same. So I'm going to initialize a new array called result which we will return to the output. Result is equal to list of nums of 0. So we have got the first element same in both places, input and output. We'll now iterate through the list for I in range of 1 comma len of nums. That is we are iterating from the second element because we have already got the first element in the output. What we will do, result dot append of nums of I, that is the element we are trying to find, right? If we are trying to find the second element for the output, we are going to get the second element from the input, then add it with the results previous element. So how this works, as you can see, we don't always have to add 1 plus 2 to get 3 and 1 plus 2 plus 3 to get 6. We can just add this 3 with this 3, right? And this 6 with this 4 to get 10. That is what is happening here. So nums of I, let's say we are trying to print the fourth element here, 10. What is nums of I? I is 4. I mean I is 3 here. So fourth position but third index. So I is 3 here. So nums of 3 will be 4, and result of 3 minus 1 is 2. What we have got into second tooth index? Second index we got 6. So 4 plus 6 would be 10. So we have everything in the result by now, result index, result list by now. Let's see how this works. Yeah, we have all the cases accepted. We have the exact same output as in the example. We can even try to submit, and let's see what the code is doing to all the test cases. Yeah, it got accepted. So this is a platform called Lead Code, guys. This platform is really helpful while we try to practice DSA. Here we have a list of problems where we can solve a lot of things, including not only lists but also high level concepts in data succession algorithms. Thank you.